It's my pleasure as the sponsor of this lecture to introduce Professor Glenn Cowan from the Royal Holloway University of London. And for those who have somewhat connected with statistics, he's a very well-known person to us because not only he wrote a textbook although it's already a little over 20 years now, I think it's still a useful textbook. It was certainly very useful at the time of lab, and he's very much involved in seminal papers on statistics. Therefore, is certainly an expert on the field we're having today. So Glenn worked at SLAC and CERN, notably in the Babar experiments, and at CERN at Aleph and now in Atlas, and he's also, since over 20 years or about 20 years, a member of the particle data group on statistics. So an authority on statistics for particle physicists, as it were. And we will have the pleasure of having 4 lectures from Glenn, and I'll invite him now to start lecture number 1 on probably the introduction. Okay, Glenn, all yours.
All right. Thank you very much, Albert. Thank you for the invitation. It's a pleasure to be with you all today. As advertised, I'm going to give 4 lectures on statistics for particle physicists. And what I'll do is I'll upload the slides typically the evening before. And so there, well, you have the Indigo page, obviously. What's going on? Now, why can't I go to the next page? Right. So here's a brief outline of what I propose to cover. In this first lecture, we'll just introduce some of the basic framework, talk about probability and parameter estimation. That's the first important task of statistical data analysis. And then tomorrow, we'll extend that to hypothesis tests and show how that can be used to set limits on parameters. And in the third lecture, we'll go on further and extend this to include different types of uncertainties, not only statistical uncertainties, but systematic uncertainties. And I'll bring in some notion of what we call experimental sensitivity, which is very important when you're in the planning phase of an experiment. And then in the final lecture, I should have just labeled this, I don't know, further topics, because I haven't really decided what to include, but my provisional plan is to include something on Bayesian methods and something called students T-regression. So that's the basic outline. Now, almost everything that I'm going to show comes from this 22-hour course that I've taught this last autumn term at the University of London. And so all the materials for the moment for that course are on that web page there, including the videos and everything. I'm not sure how long the university is going to let me keep them there. But in any case, everything I'm going to show today, almost everything, comes from that course. All right, so let me start by showing the obligatory list of books. So the one at the top is the one that Albert just mentioned, this thing that is now more than 20 years old and I have to rewrite. I think all of these books, in fact, are written by particle physicists. So these are statistical methods for particle physics. I'll point you just in particular to the very last reference, and that is the Particle Data Group's biannual tome, this review of particle physics that you can download for free. It includes sections on probability and statistics and Monte Carlo. And so anyway, those are some useful references. Let me jump right into where I think statistics sits in the sort of landscape of science, experimental science. And that is somewhere in between theory and experiment. And in particular, it provides the tools that allows you to compare the predictions of a theory with the outcomes of experiment in order to make some kind of a statement as to whether you think the theory is in agreement or can be rejected. So just to follow this line of reasoning a little bit further, suppose over on the left you have some theorists who write down a fundamental theory, say a theory of gravity, and what you would like to do then is to use this theory to make a prediction for something that could actually be measured. And so the first point I want to make is that there are a number of additional steps that have to be carried out in going from the fundamental statement of the theory to a prediction for something that you could actually measure. All right, so that includes, let me include in that the response of whatever measuring apparatus is being used. But in any case, in the starting point will be some fundamental theory, and then including a number of these steps and corrections for the measurement device, you wind up with what I'll call a model prediction. So that's what's symbolically represented by this curve here. And then, of course, we also have experimentalists who do some kind of experiments. Maybe they send protons around the LHC, or maybe they send planets around a star, and they make some sort of observations. And these result in the measured points, just symbolically here with the data points. And so what I've tried to illustrate here is that uncertainty of various kinds enters on a number of different levels. You've got uncertainty just in trying to extract the model prediction from the fundamental statement of the theory because of all the various approximations that are going to have to enter. And you're going to have uncertainty in the measurement because of the probabilistic nature of the measurement. We're just going to count a random number of events, for example. And so these measurements are going to have error bars of various, with various contributions. And so the whole idea is to try to quantify that uncertainty and to incorporate it into the analysis using probability. All right, so that's the next step, is I want to define probability. Now, probability actually has a really interesting history going back, I suppose even prehistoric people must have had some intuitive notion of probability, but the mathematical formulation was in, I believe, the 17th century in the context of gambling. But it wasn't, in fact, until the 20th century, until Kolmogorov wrote down a definition of probability based on a certain number of axioms in the language of probability theory. And so that's what I would like to show here. So this is an abstract definition. Let me consider a set S that has some elements, or I can also label the subsets of S with labels such as A and B. I will call S usually the sample space. And because this is an abstract definition, I don't even have to insist on what the elements of the set represent. But to give an example, let's say that the elements of the set could represent the possible outcomes of an observation, of a repeatable observation. And so here are the axioms that Kolmogorov wrote down. He says that for any subset A in the sample space S, we assign a real valued function, that's the probability, P of A, which is greater than or equal to 0. That's the first axiom. All right, then the sample space is, of course, a subset of itself. And so you have to assign a probability to it. And by convention, that is assigned a probability of 1. All right, and then the third axiom is a little bit more involved. It says if you consider two subsets A and B that are disjoint, that is to say their intersection is the null set, then the probability that you associate with the union of A and B is just the sum of the two probabilities, P of A plus P of B. All right, so those are the Kolmogorov axioms. And from those axioms, we can derive all of the other properties of a probability function that you know and love. There is one thing that we have to add as a sort of fourth axiom, and that is the definition of conditional probability. So you can start off with a certain sample space that might represent the set of all possible outcomes of an observation. But now suppose you want to restrict it. Suppose you're rolling a die, and so that would have outcomes corresponding to the numbers from 1 to 6. But you roll the die, and then somebody peeks and says, oh, by the way, it's an even number. All right, so now you want to know what's the probability of getting I don't know, a 3. No, it had to be a bad example. What's the probability of getting an outcome less than 3, say, given that you know it's an even number? Okay, so the way that this is then defined is the probability of A given B, say the probability of getting less than a 3, given that you know that the outcome is even, is defined as the probability of the intersection of A and B divided by the probability of B. All right, so maybe I could work this out. The probability of, let's see, A intersect B. So let's see, having the number less than 3 and the number even. Well, let's see, that's only the outcome 2. All right, so the probability of that would be 1/6. And then in the denominator, we divide by the probability of the condition that we're imposing. All right, and so that was that the outcome was even. So that's 1/2. And so you get 1/6 divided by 1/2, which is hopefully something like 1/3. Okay, so that's conditional probability, and we will make great use of that. There's a few more pieces of formalism that I want to introduce. Two subsets A and B are said to be independent if the probability associated to their intersection factorizes into the probability of one times the probability of the other. So if probability of A intersect B is equal to P of A times P of B, then A and B are said to be independent. That's just a definition. And you might say, well, why do you call that independent? Why don't you call that, factorizable? So you can see why this is independent if you think about how this works with conditional probability. You can see that suppose two subsets A and B are independent, then that means that the imposing the condition of B and calculating P of A given B, that would then just give here in the numerator for P of A intersect B, you just have the product of the two probabilities, P of A, P of B. And so the P of B's would cancel and you would get P of A. And so you can see that by imposing the condition of B, that has no influence on the probability for A. And so that makes sense that we call them independent. All right, we'll make great use of that. Let's go on. There we go. Now, sorry. Because this is an abstract definition, I haven't yet even insisted on a particular interpretation for the elements of the sample space, and I haven't given a numerical procedure that allows us to actually calculate the values of these probabilities. In order to do that, we have to introduce an interpretation. And there are two interpretations of probability that are most relevant in the physical sciences, at least. And these are what are called the frequentist interpretation and the subjective interpretation. So let me introduce those. You're surely familiar with the frequentist interpretation. Here, the elements of the sample space represent outcomes of a repeatable experiment. And we simply say that the probability associated with an outcome or a subset of some outcomes is simply the fraction of times that the outcome is in that subset in the limit that you repeat the experiment a very large number of times. So here I've written lim n goes to infinity in some very mathematical looking notation. It's clear that this is not a mathematical limit in the usual sense, but nevertheless, the intuitive notion is that if you were to somehow be able to repeat an observation in a very large number of times, the idea is that the probability would then converge to this value that we use. All right, so that's the so-called frequentist interpretation of probability. But there are other cases in which we would like to quantify uncertainty, but the notion of repeatability is just not natural or not defined at all. For example, I could ask, what is the probability that it is going to rain on January 27th, 2023? There's just a single event, it's going to happen once. So we can try to associate probability with statements that are either true or false. Here, I'll just call those hypotheses. I think this, strictly speaking, I should say propositions. But these are statements that are true or false. And I can interpret the probability simply as the degree of belief that this hypothesis is true. And if you set up a set of hypotheses such that by construction one is true and the rest are false and so forth, you can make this perfectly consistent with the Kolmogorov axioms, as is, of course, the frequentist interpretation. So both interpretations are consistent with the Kolmogorov axioms. I think it's fair to say that in statistics, as done in particle physics, that the frequency interpretation is most often useful, most often used. But the subjective interpretation is also useful, and in particular, it allows us to pose some of the really important questions, like what is the probability that magnetic monopoles exist? Well, that is either true or false, and that will not change upon repetition of any measurement. But nevertheless, that statement is uncertain, and so I would like to quantify that uncertainty with probability. Right. Now, regardless of how you interpret a probability, it has to obey an important theorem due to the Reverend Thomas Bayes, shown here. And this is a very simple theorem to derive, and so I thought we should just derive it. Now, if you go back to the definition of conditional probability, we said that P of A given B is the probability of A intersect B. You can think of intersection as the AND operation, okay? So the outcome is in A and the outcome is in B. So P of A given B is P of A and B divided by P of B. But now A and B are just labels, so we can swap the labels, and it must also be true that P of B given A is the probability of B and A divided by P of A. But then if you think about how set theory works, A intersect B and B intersect A, that's the same subset. So therefore, their probabilities also have to be equal. And so if you just take these two equations that I've written above, solve them for P of A and B, and on the right for P of B intersect A, and equate them, that's Bayes' theorem. And so then I've just taken that and I've solved it for P of A given B, and that is then equal to P of B given A times P of A divided by P of B. All right, so that's Bayes' theorem. It's fun you can Google for the original paper from the 1700s, and it's written in a language that is a bit difficult to understand, but it's quite amusing to look at. Now, very often you'll notice that here in the denominator of Bayes' theorem, and on the right, there is the probability of the condition that is imposed on the left. And it's very often convenient to be able to rewrite that denominator using what is called the, sorry, I'm having difficulty advancing. There we go. Using what is called the law of total probability. And so let me let me quickly derive this. Let's suppose that this box here represents the entire sample space. And this red kidney-shaped thing, that's B. That's the condition that I'm going to impose. I'm going to say, I know that the outcome is, say, somewhere inside B. Now let's suppose that I can chop up the original sample space into subsets A sub I, so the index I just labels the chunk, such that the union of all these A sub I's, that gives me back the full sample space. And even though I know the way I've drawn it, it might look like they're somehow overlapping, they're disjoint. The A sub I's are disjoint, right? They're non-intersecting. And so what I want to do is I want to work out a probability for B. Now what you can see is that for any one of the A sub I's, there might be a certain chunk of it that lies within B. So if that is A sub I, then the yellow guy there, that's the intersection of B with AI. And of course, you get an intersection of B with AJ and so forth. They're also disjoint. And so therefore, their probabilities add by Kolmogorov's third axiom. And so what you can say is that the probability of B is simply the sum of the chunks of the parts of the AIs that lie inside B. That's grosso modo the statement of the law of total probability. And here I've written that down in just slightly more formal mathematics. But so here I start by saying that B is the union of the B intersect AIs. And then by Kolmogorov's third axiom, I say that the probability of B is equal to the sum of the corresponding probabilities. But then if you go back and you think about the definition of conditional probability, so P of B given AI, that is defined as P of B intersect AI divided by P of AI. And so if you just solve that for P of B intersect AI, you can see that that's none other than what I've written here on the final line. Okay, so P of B is equal to the sum over all of these subsets AI, P of B given AI times P of AI. And so having arrived at this expression for the probability of B, the condition that I impose, I substitute that into the denominator of Bayes' theorem, and that gives me the form of it, which is quite useful in many applications. All right, so here is an application, and somehow by tradition, it's always supposed to be a medical test. So let's suppose that within some population of people, there's a disease that has a probability, you have a probability to have the disease of 1 in 1,000. And that means that the probability not to have the disease is 1 minus that. Those two numbers have to add up to 1. I'll call these the prior probabilities. These are the probabilities to have the disease before any test is carried out. And don't ask me how I know these numbers, but let me suppose that in some population or subpopulation, we figured out that the prior probabilities for somebody to have the disease are 1 in 1,000. Now let's suppose you come up with a test for the disease, and the outcome of the test is just a plus or a minus. It only has a binary outcome. Some tests might give you an actual number, but let's suppose this test just gives you a positive or a negative result. So how do we characterize the accuracy of this test? Well, we can give the probability to obtain a positive outcome, a positive result, given that the person has the disease. And let's suppose that that's 98%. That means that the probability to get a negative result, given that the person has the disease, has to be 2%, because there's only a positive or negative outcomes. That has to be one of the two. So those two probabilities have to add up to 100%. And then that, of course, is insufficient to characterize the accuracy of the test. You also have to give the probabilities to get positive and negative results for a person who doesn't have the disease. And of course, those are completely different numbers. Those don't have to be, the 98 and 2. So let's suppose that the probability to get a positive result, given that somebody doesn't have the disease, that's not 0 in general. Let's suppose it's 3%, still quite low. And so therefore, the probability to have a negative result, given that the person doesn't have the disease, that has to be 97%. Those two numbers have to add up to 100, obviously. All right, so you go and you take the test and you get a positive result. What is the probability then that you have the disease? How worried should you be? Because after all, if you look at these numbers, you would say, well, it's a pretty accurate test. You can't just say it's 98% accurate. That's insufficient to characterize the test. But nevertheless, if you look at these numbers, you would say it's a pretty accurate test. So just think intuitively, what's the probability that you have the disease? Well, what do we want in terms of Bayes' theorem? We want to know the probability that you have the disease given that you got a positive result on the test. And so if we use Bayes' theorem in the numerator, we have to have P of plus given disease times the prior probability to have the disease. And then in the denominator, you would want to have P of plus, but that wasn't one of the ingredients that we have. And so we can use the law of total probability, though, to express that as P of plus given D times P of D plus P of plus given no disease times the probability that you don't have the disease. And when you plug in the numbers, you get 3.2%, which is still quite low. It means you're probably okay. And so that's a rather surprising result. But if you think about it, the reason that this happens, of course, is that this, what we call the posterior probability to have the disease given a positive test result, after the test, that's proportional to the prior probability. And that prior probability was only 1 in 1,000. And so having obtained a positive test result, your probability to have the disease has jumped from 1 in 1,000 up to 3.2%. So it's gone up quite a bit, but it's still quite low. Now, it's one of the things that's quite interesting about this example, other than the surprising result, is that we don't have to insist necessarily on the interpretation of probability in order to do this calculation. Bayes' theorem has to hold no matter what. So you might say, well, subjectively, I want to use subjective probability and to evaluate my degree of belief that I have the disease. Well, then it would be 3.2%. On the other hand, you might, your doctor's viewpoint is that he or she looks at a large number of people, and they would simply say that, well, the fraction of people in that circumstance who get the positive test result, 3.2% of those people will have the disease. Right? So Bayes' theorem holds regardless of the interpretation. Now, I don't want to spend too long just on woolly philosophical matters, but if you will permit me to show just two more slides on these two different interpretations of probability, it's important because they lead to two quite different ways of doing statistics, what are called frequentist statistics, using frequentist interpretation, obviously, and then the subjective probability is used in what's called Bayesian statistics. And so I want to give just two slides where I make a few more comments on those two main schools of statistical inference. Now, in frequentist statistics, probabilities are only associated with the data, only associated with outcomes of repeatable observations. And the shorthand that I will usually use in my slides is some Latin letter like X. So that's just going to symbolically denote the outcome of some repeatable measurement. And we interpret that probability as the limiting frequency of such outcomes. So in that context, trying to say something like the probability that string theory is true, or the probability that a particular physical constant lies between fixed limits, those probabilities are either 0 or 1, but you don't know which. And so you might say, well, hang on, that means that how can I use frequentist statistics to address really the important questions, like, is string theory true? After all, frequentist statistics, what does it tell you? It only tells you what to expect for hypothetical repeated observations. How do you say in that context whether a theory like string theory is preferred or not? Well, roughly speaking, we say in frequentist statistics that a certain theory is preferred if that theory predicts a high probability for data that are in some sense like the data, similar to the data that we actually observed. So that's kind of a convoluted way of having to state under what circumstances a theory is favored or disfavored. And so you might think, well, I don't want to use that. I want to use Bayesian statistics. So let's look at the other school of statistical inference. So in Bayesian statistics, we extend the interpretation of probability to include subjective probability for the hypotheses that we're interested in. And so what we would like to find is the probability for some hypothesis H, given that we see some data X in our experiment. That's the object which is going to summarize for us all of our knowledge about whether we think the hypothesis H is true or not. And so how do we get that? Of course, we use Bayes' theorem, hence the name Bayesian statistics. And so Bayes' theorem says that P of H given X is equal to P of X given H times the probability of H, which I've written here with a different letter, pi of H, divided by P of X. And here in the denominator, I have replaced P of X by the law of total probability. In the previous derivation, I had that written as a sum over discrete A sub i's. And here, if I'm assuming that the letter H is continuous, then that sum gets replaced by an integral. So in the denominator here, you'll either have a sum or an integral over all the possible hypotheses. So let me just say a few more words about the ingredients in this equation. As I said, pi of H, that's what's called the prior probability. That expresses your degree of belief that the hypothesis H is true before you did the experiment. All right. And then the result that we're trying to get is what's called the posterior probability, the degree of belief that H is true, given that you got the outcome X. And then this expression here, P of X given H, that is what's called the likelihood. All right. That's the probability to see the data given the hypothesis, and that's what really defines the hypothesis in question. All right, so you say, all right, how do I use this? In order to, you might know how to write down P of X given H, because that's what a theorist would tell you. That's what defines a particular particle physics theory, say. But how do you get the prior probability? What's your degree of belief in the hypothesis before you did the experiment? There is no general rule, at least provided within the framework of Bayesian statistics, that tells you what that prior probability is. It's necessarily subjective. And so that's kind of interesting. It says that Bayesian statistics doesn't even predict in a unique way these probabilities. It only tells you how a prior probability would get updated in the light of the data. And in that sense, Bayes' theorem has a sort of if-then character. It says, if your prior probability in a particular hypothesis was pi of h, then in the light of the data, having seen the data x, Bayes' theorem tells you how that degree of belief should be updated into this posterior probability. All right, so that's important to realize that the Bayes' theorem has this sort of if-then character. There's no general prescription, however, for these prior probabilities, or what I'll just call the priors. All right, so that's enough, I think, philosophizing on the different ways of doing statistics. Let's get in now to the first major topic of today, and that has to do with the parameter estimation. But before I go there, I need just a few more slides of formalism, and that is I wanted to say again more concretely what I mean by a hypothesis and a likelihood. Like, this is really more or less what I said on the previous slide, but let me just go through this. Let's suppose that the result of an experiment is some collection of numbers that I will denote by a vector x. All right. And what I mean by a hypothesis, or a simple hypothesis, is a rule that assigns a probability to every data outcome. All right, so P of x given h, that defines my model. And when I say I'm talking about a particular hypothesis, then that implies that I was able to write down such a rule, right? It's not just a statement that's true or false. It implies an assignment of probabilities to the outcomes that I think I could measure. Now that term, as I said, is what's referred to as the likelihood of the hypothesis. If you regard this just as a function of the hypothesis and you regard the data as fixed, then this quantity is what we call the likelihood of the hypothesis. Now, very often we deal with a family of hypotheses where we use a numerical label for the hypothesis in the sense of a numerical parameter. And so usually I'll use a Greek letter for such parameters. So then I would write P of x given, and I'll write whatever parameters there are. And so that means that in order to actually say what the probabilities for the data are, I have to specify the value of the parameter. Right? So this is not a simple hypothesis, it's what I'll call a composite hypothesis. But again, if I look at this as a function of the label for the hypothesis as a function of the parameter, I'll call that the likelihood function. It's a little bit deceiving here when I write P of x given theta is L of theta, because when I write L of theta, it makes it look like the data has somehow disappeared. You have to keep in mind that this likelihood function has the data stuck in there, but I'm only viewing it as a function of the parameter. All right. So, for the likelihood, we treat the data as fixed. Note, however, that this likelihood function is not a probability density for the parameter. It's different. It is a probability, but it's a probability for the data, not for the parameter. All right, so that's the likelihood and the likelihood function. Now there's a special case that I want to mention, and that is the likelihood function for what is called an IID data sample. So IID stands for independent and identically distributed. So let's suppose that we have n independent observations of some quantity x, so x1 through xn. And let me suppose that this x, this random variable x, follows some probability density function, PDF, f of x, and that depends on some parameter theta. All right, so I observe this entire sample of x values, and they're all independent. And I want to then write down the joint probability for all of them. Well, because I've insisted here that they're independent, then remember the idea of being independent is that the probabilities factorize into the product of probabilities for each of the individual measurements. So that means that the joint PDF for this entire sample is just given by the product of f of x sub I, where this is the PDF for just one of the x's. All right, so that equation there is the hallmark of an IID data sample. All right, so the likelihood function is just the probability for the data given the parameter. It's just this guy here on the left. And so that means that it is then, in this case, given by the product of the PDFs over each element, evaluated with each element of the observed data. And again, then you treat these xi's as constants, and you look at this, you treat it just as a function of theta. Sometimes I'll write theta with a vector if I want to emphasize that there's not just one parameter, it could be a vector of some number of parameters. All right, so that's a formula for the likelihood function. Now, let's get into parameter estimation. So as I said, when I say the parameters, I'm talking about any constants that characterize the PDF, and in doing so, essentially label the hypothesis. So the notation that I will use is, as I said, I'll almost always use a Latin letter for the data and a Greek letter for the parameter. And I'll usually write the data, the random variable, to the left of a semicolon and the parameter to the right. And in other cases, instead of the semicolon, I'll just write a vertical bar, and then it looks like the notation of conditional probability. And that's essentially equivalent. So here's an example. Let's suppose that the PDF that I'm talking about is an exponential distribution. And so let's suppose that this parameter theta is not known. It could x could represent the measured lifetime of an unstable particle, and theta represents then the mean lifetime for that type of particle. And so let's suppose that you have a sample of observed values. And what we want to do is we want to form some function of these data values that represents an estimate of this unknown parameter. And so what I will do is I will write that with that whatever function I come up with, I'll call that the estimator for theta, and I write that with a hat. And so what's important to keep in mind is that estimators are functions of the random variable x. The parameter theta in the frequentist context is not a random variable. It's an unknown constant. But the estimator for the parameter theta hat, that's a function of x, and a function of a random variable is itself a random variable, right? So if it has a hat, it itself is a random variable. If it doesn't have a hat, in the frequentist context, it's an unknown constant. Now, physicists are not so great at distinguishing between a function as a mapping and the value of that function when you evaluate it with a particular argument. Now, in cases where it's important to make that distinction, I will say estimator for the function, and I will say estimate for the value of the estimator evaluated with a particular data set. Usually that's not too critical. All right, so how do I write down this function? One of the things that's important to realize is that in fact, there's no golden rule within frequentist statistics for what function we choose as the estimator. Estimators can have different properties, such as bias and variance, and we have to evaluate the functions on the basis of those properties. I hope I didn't lose a slide where I'm going to explain the bias and variance. I think it's coming up. But the technique that I want to introduce for constructing the function is the following. It is what is called the method of maximum likelihood, and it leads to the so-called maximum likelihood estimators, or MLEs. I used to always say ML for maximum likelihood, and now everybody understands ML to mean machine learning, and so that just leads to confusion. So I'll call them now MLEs for maximum likelihood estimators. And they're defined in the following very simple way. You simply say that the maximum likelihood estimator is the value of the parameter for which the likelihood is a maximum. Now the value of the likelihood, the value of the parameter that maximizes the likelihood will also be the value of the parameter that maximizes the log of the likelihood, since the logarithm is a monotonic function. And it's usually easier to work with the log of the likelihood. And so, in fact, we call that always the log likelihood. So if you look at the log likelihood as a function of the parameter, in general, it can come up and go down. And so that point right there defines the MLE, all right, theta hat. So that's just a fancy mathematical way of writing that. Theta hat is the value of theta that maximizes the likelihood. So in general, the likelihood function can in fact have multiple maxima. And if that's the case, then you would define the MLE as the highest one. They're not guaranteed to have any particular optimal properties, but I will argue that in practice, they're very good. Now, coming up next, I hope I haven't lost a slide. I think I have somewhere. I've somehow magically dropped a slide. That's all right, I don't need it. I'll stick it back in the slides later. I was going to explain that the properties of the estimators that we want to focus on have to do with the bias and the variance, and I will explain those in just a second. So let's do an example. The example I want to consider, in fact, is the one that I already alluded to, namely an exponential PDF. So here, let me call the random variable t, and let me call the parameter tau. And so here the PDF is just 1 over tau e to the minus t over tau. And let's suppose that I have an IID data sample, t1 through tn. And so that means that the likelihood function is found simply by taking the product of those PDFs each time evaluated with the ith measurement. All right, so that's the likelihood function. And to construct the MLE, I simply have to find the value of tau that maximizes L of tau. And as I mentioned, it's easier to work with the log of the likelihood function. And here you can see why. And that's because by taking the log, it converts this product into sum of logs. Right? And furthermore, PDFs very often include exponential terms. And so then by taking the log of the exponential, it simplifies. And so here then is the likelihood function, the log likelihood function that we have to maximize. And so maximizing that is simply a matter of taking its derivative and setting that equal to 0, and then solving that equation for tau. And when you solve it, you write it with a hat, because that's our MLE. And in this particular case, so I'm just skipping 2 lines of mathematics there. In this particular case, the MLE turns out to be none other than the arithmetic average of the measured values. And so here on the right, I show a quick little Monte Carlo test just to illustrate what this all means. I wrote a Monte Carlo program where I used tau equals 1 as the true value, and I generated 50 values representing the data set T1 through T50. Right, so those are the tick marks. And then if you evaluate the MLE with those 50 values, you get tau hat. So this is now the estimate of 1.062. Right, so that then is the PDF when evaluated with the MLE. All right, so that's an example of what we would call unbinned maximum likelihood. Now, the properties of the estimators that we want to focus on are what are called the bias and the variance. And so the bias of an estimator is, this is what was on the slide that went missing. So let me just write this. The bias of an estimator is defined as the expectation value of the estimator minus the true value of the parameter. And so I want to work that out for the estimator that we're using now. And so in order to do that, I first need to know the expectation value of an exponentially distributed random variable. And so that's the definition of the expectation value. It's just the random variable times the PDF integrated over all values of the random variable. And so that integral gives you tau, right? So the expectation value of t is just equal to tau. The other property that we want to focus on is the variance of the estimator. So the variance of tau hat, or equivalently, the square root of the variance, which is then the standard deviation of tau hat. And so I should sketch here. The point is that if you look then at repeated measurements of this estimate of tau hat, they're going to follow some distribution. Voila. And I would like that distribution to be centered about the true value. And that's what the bias will tell me. All right, so in other words, if the expectation value, if the center of gravity of this PDF for tau hat is equal to tau, then that means that the bias will be 0. Whereas if the PDF for tau hat were to be, something like that, that would be an example of an estimator that has a non-zero bias. And furthermore, we want this estimator to be as accurate as possible. And so that means you want it to be as narrow as possible. So you want the estimator to be to have a narrow PDF, right? And so the width of this PDF, of course, is reflected by the standard deviation. All right, so sorry, those are the sketches that were on the slide that somehow went missing. But let's work out now these quantities, namely the bias and the variance of tau hat. All right, so here's the MLE. Just in this case, it turned out to be the arithmetic average of the t sub i's. And so that means the expectation value of tau hat, let me just substitute that in to my expectation value operator. When you take the expectation value of a linear combination of quantities, the constants get pulled outside, and the expectation value of the sum is the sum of expectation values. And the expectation value of each of the TIs is just equal to tau. And there's n terms in the sum. And so that means that the expectation value of tau hat is just equal to tau. And that means that the bias is 0 in this particular case. So that means that the PDF of tau hat is centered about tau. All right, that's what we mean by an unbiased estimator. Then we can work out the variance of tau hat. And so we substitute in the variance. So we substitute in the tau hat into the variance operator. There, if you think back about the definition of variance, it involves taking the random variable and squaring it. And so that means that when you pull out a constant, it gets squared. And because the t sub i's are independent, it means that the variance of the sum is given by the sum of variances, right? The variance of t is equal to tau squared. And so therefore, this variance of tau hat is equal to tau squared over n, right? There's n terms in the sum, so that one factor of n cancels. All right, so that's the variance of tau hat. And so therefore, its standard deviation is just the square root of that tau over root n. That gives the standard deviation of tau hat as a function of the true and unknown parameter, as a function of tau. If you really want a number, well, then you want an estimator for the standard deviation of the estimator of tau hat. And you can get that just by evaluating it with the MLE for tau itself. Right, so that way you get a number out. It's important to keep in mind that the standard deviation of an estimator is a function of the true and unknown parameter. All right, I hope that made sense. Let's go on. In that particular example with the exponential PDF, the ingredients were so simple that it was possible to work out the bias equal to 0 identically, and we had a closed form expression for the variance. Now, very often that's not case, and that's not the case. The mathematics is too difficult to even write down the MLE in closed form, and we're certainly often not going to be able to write down a closed form expression for its variance. And so there is a simpler procedure that I want to introduce. And to do that, I want to start by introducing something called the information inequality. So this is sometimes called the RCF, or Rao-Cramér-Fréchet inequality. And this sets a lower bound on the variance of any estimator, not only the MLE, but any estimator you can write down will have to have a variance which is greater than this thing on the right, called the minimum variance bound. So here's the version for a single parameter, and then there's the corresponding version for multiple parameters, which is in the extra slide somewhere. But let's just discuss the one parameter version to start with. The information inequality says that the variance of any estimator theta hat for a parameter theta has to be greater than or equal to, here in the numerator, we've got 1 plus the derivative of the bias with respect to the parameter. All right, so that's the bias as I introduced it earlier. And then in the denominator, we have the expectation value of the negative of the second derivative of the log likelihood function. All right, so here, this expectation value of anything means that you take whatever that thing is and you multiply by the probability for the data and you integrate over all data values, right? So that's, remember, just my general definition of what I mean by an expectation value. So this information inequality can be proved without too much difficulty in my textbook. So this SDA refers to my book. There's some exercises that are on this website here. And if you go to that file there, one of the problems is to prove the information inequality. But the problem is posed in such a way that it walks you through it step by step. So if you're interested in seeing how the information inequality is proved, I would invite you to look at that exercise. Sometimes we define what's called the efficiency of an estimator as the minimum variance bound divided by its actual variance. I hope I've done that right. Yes, because that's going to be less than 1 in general. But if you can construct an estimator whose variance is equal to this minimum variance bound, it is then said to be efficient. Right. So let's work this out for the example that we just had. Let's find out the MVB, the minimum variance bound for this estimator for the exponential parameter. We found the MLE was just given by this arithmetic sum. And we showed that the bias was identically equal to 0. And so therefore, the derivative of the bias is equal to 0. If you go back to the log likelihood function and just differentiate it twice, this is what you get for the second derivative. Right. And then when we take the expectation value of this, we can exploit the fact that the expectation value of all of the t sub i's is equal to tau. Right? And so then if you work that out, it comes out trivially that the expectation value of this second derivative is minus n over tau squared. All right, and the MVB is then going to be minus 1 over that. So the minimum variance bound is tau squared over n. And that's exactly what we found earlier, 2 slides ago. And so in this particular case, the maximum likelihood estimator is efficient. It's not always true for MLEs, but it is in this particular case. Now, I see I'm running low on time, but I hope I have time to just run through some final properties of MLEs in a particular limiting case, namely in the case where the number of observations in the data sample gets very large. So let's suppose that we have an IID data sample with n observations. I'll call that the size of the data sample, right? And in the large sample or asymptotic limit, which is to say when the number of observations becomes very large, and assuming what are known as regularity conditions, one can show that the likelihood and the MLE itself have a number of important properties. Now, these regularity conditions are a bit complicated and difficult to state, but let me just summarize the important ones here. So I'll say the regularity conditions include the following. The boundaries of the data space cannot depend on the parameter. The parameter cannot be on the edge of the parameter space. The log likelihood function has to be differentiable. And the only solution to this likelihood equation is the theta hat. Now, we could spend a long time on those properties, but let me just state those as the important ones. Now, what I'm going to show on the following slides that I'll run through now just to finish up, these are the large sample properties of MLEs for the single parameter case. But then the corresponding properties also hold in the multi-parameter case, and there is some information on that in the extra slides. So first property, the log likelihood function becomes quadratic, which is to say that the shape of the likelihood function as a function of the parameter becomes Gaussian in shape, right? It becomes increasingly peaked around the true value of the parameter. That doesn't mean, I've said this previously, that doesn't mean that the likelihood function is a PDF for the parameter. It does become increasingly peaked about the true value of the parameter, but it still is not a PDF for the parameter itself. So if the likelihood function has a Gaussian shape, then the log of the likelihood becomes parabolic. That's somehow the important property that we're going to use. All right. In the large sample limit, the maximum likelihood estimator converges to the true parameter value. Uh-oh, I better define what I mean by convergence. This is what's called convergence in probability. All right, so formally this means that for any epsilon greater than 0, and in the limit that the number of observations becomes very large, then the probability to have any departure greater than epsilon of theta hat from theta, that probability goes to 0. The MLE is said to be consistent in that sense. That's what it means for an estimator to be consistent. Estimators in general are consistent. That's not usually a major concern when choosing an estimator. All right. In the large sample limit, the MLE is unbiased. All right. So in the limit that the number of observations becomes very large, the expectation value of the MLE minus the true value of the parameter, that goes to 0. So in this example that we just looked at for the exponential parameter, the bias was 0 regardless of the sample size. When you say that you have an unbiased estimator, that means for any sample size. But in general, the MLE will be unbiased in the limit when the data sample gets very large. All right. In the large sample limit, the MLE's variance approaches the minimum variance bound. All right, so that means that the large sample limit of this variance is just given by the MVB as I've written on the right, and the bias goes to 0. So in the numerator, I've gotten rid of the bias term. So the MLE is said to be asymptotically efficient. All right. And furthermore, the MLE's distribution itself, remember the MLE is itself a random variable because it's a function of the random data. So the PDF of the MLE becomes Gaussian, all right, where the variance of the corresponding Gaussian is the minimum variance bound. And you can just see by looking at this Gaussian PDF that its expectation value is equal to theta. So that tells you from this distribution for theta hat that theta hat is an unbiased estimator for theta. So here's just to illustrate that, here's the, let's go back to this exponential example. Here's the PDF of tau hat. And so what I've done is I've repeated the Monte Carlo experiment a large number of times, each time with a sample size of 100. And then this histogram, the blue histogram, represents the estimates that I obtained. And then I've just overlaid with that a Gaussian PDF, and lo and behold, they agree quite well. I'm over time, so let me finish up really quickly. Here's just to illustrate that a little bit better. It's the same histograms. It's the distribution of tau hat for 4 different sample sizes for 5 observations, 20, 50, and 100. And so you can see that if you have a relatively small data sample, that the PDF of the estimates has a hump, but it's not really very Gaussian. But as the sample size gets larger, indeed the PDF of the estimator becomes increasingly Gaussian. Now, even if I have further stuff, I think I'm going to draw a line here, and we'll pick this up tomorrow because I've just run too far over. So what I'm going to do next week is I'm going to finish up with a final technique for determining the variance of estimators using by exploiting these large sample properties. And let's pause now. So, Albert, do you agree? I should.
Yes, I think it's fine. We
Fine to stop
here,
now. I don't
yeah.
want to exploit people's timetables.
Yeah,
Howard,
correct.
do we have time to take a few questions, or how should we
Absolutely. We
do
have
it?
a few questions. First of all, thanks, Glenn. You can't get the round of applause as you would have gotten in the room, but imagine it happened. And second, I would say that the next lecture is not next week, but actually tomorrow, just if
Yes.
no confusion. And after having said that, yes, there is time for questions. So you can either put them in the chat if you have no means of speaking, or raise your hand, and then I will invite you to ask your question. So any questions, please? Mohammed.
I just have a question on the last kind of note you made about the Gaussian approximation. First of all, thank you for the slides and lecture. It's very useful. So here you show on the last slides that you keep here, you show like a different number of sample sizes and how it goes closer to a Gaussian, but in sort of a complex analysis where there's multiple parameter dependence, how do you judge whether, whether you are well within that Gaussian approximation and you can start using it or not?
Yeah, good question. Unfortunately, there's no really general useful theorems that will tell you how close to the asymptotic limit you are. And so what we end up doing in practice is doing Monte Carlo tests to try to determine whether or not the asymptotic approximation is sufficient. So no, I'm afraid that in general there are no tools that will tell you in a simple way whether or not the asymptotic approximation is appropriate. That being said, even though this holds only in the limit when the number of observations becomes infinitely large, what we find in practice is that these asymptotic approximations become useful already for very small, for just a few observations. So here, I don't know, here it looks like, for 20 or 50, that this Gaussian approximation would be adequate. That will depend a little bit on how far out into the tails you need this approximation to be adequate. All right, it will start to break down. If I were to blow up this sketch and maybe show it on a logarithmic scale, you would see that the approximation is going to break down in the tails. But to specifically answer your question as to how do you know, there I don't know of a general theorem for that.
Thank you.
Sorry, I was muted. Other questions, please? If there are. Adrian, can you say your question itself, or I should read it for you?
Can I look at the chat window?
If you see it, Glenn, then you can immediately.
Yeah. I'm not seeing the chat window is the thing.
Okay, I can tell you.
Oh, no, hang on, please read. So let's see. In which cases do we have to deal with non-IID variables? Yes, so you can imagine a situation where you might measure some number of quantities for an individual event. And so, for an individual proton-proton collision, you might measure the PT of some of the jets and their directions and energies and so forth. And if those are all characteristic of an individual event, then they're not independent. And so if what you mean by is that your observation is the observation of an individual event, then the collection of numbers that you measure for that event, they're not independent. So you would not be able to just express their joint probability as the product of the probabilities for each of the individual attributes, each of the individual quantities. But one of the features that we always use, at least in particle physics, is that we treat every individual event as independent. So if that's the type of analysis, then we always have an IID data sample. right? Because we treat individual particle collisions as independent. So does it fundamentally alter the mathematical formalism? It fundamentally alters the way that you have to write down the joint probability for the data. But once you have that, that's the likelihood. So even though there might not be factorizable in the way that it would be for an IID data sample, once you have P of X given theta, then that gives you the likelihood function. And the method of maximum likelihood and all the other techniques that I'm going to discuss, they would go through as before.
Okay, thank you. And if you see the next question there from Tianyi Yang, then that I think.
I would like to know if for large enough loops, Bayesian posterior probability will not depend on the prior input. Ah, that's a very good question. So the idea now is the following, is that if you look back at Bayes' theorem, let's see if I can go back to an earlier slide where I have Bayes' theorem somewhere. You will see in Bayes' theorem that the likelihood always appears, the prior always appears multiplied by the likelihood. And so what can happen now is the following. As the sample size gets larger, so as the data becomes more accurate, if you will, we saw in that final example that well, it wasn't directly from the final example, but the likelihood function becomes more and more narrow. So if you imagine that if you start with a prior, let me exit from my slide now. Is my video on? No, it's not. I'm going to stop sharing.
I don't see it.
But you can see my Blackboard now, right?
Right.
All right. Watch this. Is this visible, Albert? Anybody?
Yeah, that can be seen.
All right, all right. So the point is the following, is that let's suppose that you start off with a prior pi of theta. Let's use theta to represent the parameter. And you have some likelihood that looks like this. So this is going to be P of X given theta. Sorry, let me. As long as this prior is broad relative to the likelihood function, then you can see that the product of these two terms is going to be insensitive to the details of the prior, as long as it's relatively broad. So in other words, if this goes to 0 at some rate, or if it goes to 0 at some slightly different rate, maybe it's like that. The product of these terms connected together with the likelihood is going to result in roughly the same thing. And that becomes increasingly true as the likelihood function becomes narrower. So the likelihood function will become increasingly narrow for large n, means that L of theta becomes narrow. And in that limit, what happens is that the product of the likelihood and the prior decouples from the detailed form of the prior, as long as the prior is sufficiently broad. Sorry, my chair is here probably getting in the way. I hope that made sense. The one syllable answer to your question is yes. Yeah. In this sort of limiting situation where the data becomes increasingly accurate, the posterior probability then becomes insensitive to the details of the prior. Now that will not be true if you were to choose a prior which is not broad, right? If somebody were to say, no, my prior degree of belief about the parameter isn't this broad thing, but it's a delta function right here, because that corresponds to my favorite theory, well, then the product of a delta function and any likelihood is always just going to be concentrated there. So you have to start with an open mind. You have to start with a prior which is sufficiently broad in order for that statement to hold. All right, hope that made sense.
Okay, thank you. I don't know if you still have the chat that you can see.
Let me go.
or
No, I
was that
closed
more
it. Let
questions?
me do that.
Okay, then I'll read it to you. So this is a question from Glenn with
All right.
double N, so another Glenn. You introduced MLE as a technique for parameter estimation. This works well and is also intuitive. Are there alternatives to MLE? And if so, are they consistent with whatever estimates we get from
Yeah,
MLE?
very good question. So as I mentioned, there's no golden rule for constructing an estimator. We simply have to investigate their properties, such as their bias and variance. And in general, maximum likelihood estimators can have a bias, and they will have a certain variance. You might want to choose an estimator that gives you a different trade-off between those two quantities. You can't choose an estimator that automatically gives you minimum bias and minimum variance, because those two properties are conflicting. It can happen under certain circumstances that the estimator that you get from the method of maximum likelihood might have zero bias, but a very, very large variance. And so what you can do is you can construct an estimator that accepts a small bias in exchange for a substantial reduction in the variance. And this is what's done very often when we talk about what's called unfolding, and in particular problems that have large numbers of parameters. So that would be an alternative to the maximum likelihood estimator, is what's called a regularized estimator, where you accept a small bias in exchange for a large reduction in variance. I'll mention one other method, and that is that the method of least squares is very often used as a technique for constructing estimators. And it is equivalent to the method of maximum likelihood under particular circumstances, when the measurements are Gaussian distributed. But very often we use the method of least squares even in cases where that's not quite the case. Usually it's at least an approximation. So there can be numerical reasons why a method other than the method of maximum likelihood might be preferred, just because it's numerically very simple. And the method of maximum likelihood would be an example of that.
Okay, thank you. I'm going to take this now as the last question for today. There are 3 more lectures, so we have more time for questions in the next day. So this is a question from Tuan Fang. Why is it that we maximize the probability of obtaining the data given the parameter with respect to the parameter, but not the degree of belief in the parameter giving the data, namely P, the probability for theta given X?
Yes, yes. Okay, so what I've explained is the frequentist method of constructing an estimator. And you could then ask, well, what's the corresponding Bayesian way of doing it? And what's somehow the point of contact? And I will return to that in the 4th lecture. And what I can tell you is that the method of maximum likelihood, the MLE, will coincide with the peak position of the Bayesian posterior PDF under particular circumstances, namely, if you took the prior to be constant. So if you had a parameter theta, and if you took the prior degree of belief for theta to be constant, so as broad as you could possibly imagine, under those particular circumstances, what you find is that the peak position of the Bayesian posterior PDF coincides with the MLE. Under other circumstances, they're different. But we'll come back to that in the 4th lecture.
Okay, good. So there are still a few questions on the chat, but I think either if you see them, if a quick answer, you can give them. Otherwise, we have to wrap up at some soon here.
Okay.
Or you can come back to that during the lectures as they proceed.
I think what's probably best to do is let me take those either tomorrow if people want to email me questions, that's fine too. You know, but maybe let's wrap up now.
Okay, good, great. Okay, thanks. Thanks for the lecture again and for the discussion session. And to everybody in the room, thanks for joining, and hope to see you again tomorrow, same time, 11 o'clock Geneva time, and hopefully still with good weather outside. All right. Thanks, everybody. We're closing this meeting now.
Bye-bye.
Bye.
Bye.